Let's get started with our fractional factorial with interactions example. In this case, it's a machining experiment, and we want to increase the tool life. Now, in this particular experiment, we have 5 factors: XY feed, stack height, speed, bit type, and suction foot type. We've already determined that we want to study the combined effect of stack height and speed. So an efficient example that we could use for a design layout would be this 5-factor, 1 interaction in 8 experiment runs. So we start by placing the interactions. So we have these options for allowable 2-factor interactions. You can choose just one of these. So if we select B times C, then what we're going to do is we're going to put the stack height in column B, we're going to put the speed in column C, and then we'll put the other factors, XY feed in A, we'll put the bit type in D, and the suction foot in E. And once we've done that, we understand how we're going to lay our experiment out. This is important because we want to tell Minitab exactly what we're doing. All right, even though Minitab thinks we know what we're doing, we need to make sure we tell them so that Minitab will understand exactly the way that we're going to run this experiment. So now go ahead and open up Minitab, and you can open up the Fractional Factorial 1x.mpj, which is a Minitab project. And then once you do that, what I would like you to do is to create an extra worksheet. So let's just start with a worksheet. This one, when you open it up, has all the data in it and everything, and we'll get to that when we go to do the analysis. But let's start with, let's design this experiment in Minitab. So we'll start with a brand spanking new worksheet. And then what we're going to do is we will go to the Stat menu. We're going to go to Design of Experiments, Fractional Factorial, and we're going to create a factorial design. We're going to choose that. Now, the number of factors that we have is 5. All right, it's a 2-level design. We can display the available designs, and we're going to be running an 8-run experiment. All right, and if we look at that, Minitab has said that that's resolution 3. Oh, a red sign, stop, don't use that. Well, we're going to use it because we know what we're doing. All right, Minitab assumes that you may not know, so they're trying to push you into full factorials, and we're not going to do that. Because a full factorial on 5 factors at 2 level settings would be 2 raised to the 5th power, or 32 possible combinations. We're not going to do that. All right, so we're going to just say OK to that. And the designs that are available to us is this quarter fraction, 8 runs, resolution 3. All right, we know when we go to design this experiment that we have 3 data points per run. All right, because we've already actually collected the data. And this has already actually been run, but let's say that, you know, we were designing this before we started, and we said, all right, we're going to have 3 repetitions per run. We're going to select that. All right, there's going to be 1 block. There's going to be no center points. And we're going to say OK. All right, so now it knows that we're going to have 3 repetitions per run. All right, so now we're going to go to factors, and we're going to type in our factor names, and we know that factor A is going to be the XY feed. All right, and the XY feed is numeric, and the low setting is 40 and the high setting is 60. All right, in column B is the first of our interaction columns. B and C are the combined effect of the interaction we're going to study, and this is going to be the stack height, and we're just going to call it stack. And that, once again, is numeric, and the low setting is 0.1875. I'm going to tab over, and the high setting is 0.25. All right, factor C is speed. That's also numeric. The low setting is 30, and the high setting is 40. Now, factor D is the bit type. Type that in, bit type. Now, bit type is not numeric, it is text, and we're going to select text. All right, and we know that our low setting on text is going to be A, and our high setting is going to be B. And then the last but not least is the suction foot. We'll just call that suction. And it is also text, so I can just type in T for text. And the low setting for that is BB, which is one of the types. And the other one is SR. All right, so that is our factors. And we're going to say OK. All right, now options. All right, here we would normally just randomize the runs, but we are not going to do that because I want what you to create look the same as what I'm creating, so we're not going to randomize the runs. We are going to store them in the worksheet. We'll say OK. The results, all right, we would like to have a summary table, and we'll say OK. All right, so now we're ready to actually generate the design. So I'm going to press the OK button. It'll generate the design. All right, we'll go back to our worksheet. Okay, show the worksheets folder. Go over here to the worksheet. All right, so here's our worksheet. So the standard order and the run order are exactly the same. Now the standard order, that's the unrandomized order. And the run order would be the one that we would randomize. But in this case, we're not randomizing it. But if you look at what's going on here, so we have 1 through 8, and it is really the complete experiment 1 through 8. So that's one replication, and then it'll get repeated again in 9 through 16, and then it'll get repeated again. So what we want to do is we want to resort this. So what we're going to do is we're going to create a sort column, and the reason for doing this is we want to make the data entry easy. So we're going to type in sort, and then what we're going to do is we're going to say we have run number 1, 2, 3, 4, 5, 6, 7, and 8. And now what we're going to do is we're going to copy 1 through 8. I'm going to copy that. I'm going to paste it again. And I'll scroll down here, and I'm going to paste it again. All right, so now I've identified all my run 1s, my run 2s, 3s, 4s, and 5s. And then I'm going to go ahead and sort this whole thing so I can put all my 1s together, my 2s together, my 3s, my 4s, my 5s, my 6s. Then when it comes time to do your data entry, you'll be able to just key in the data points for run number 1, then run number 2, number 3, etc. And typically, when we're running the experiment, we're going to set up a condition, and we're going to repeat that condition as many times as we need to generate the required amount of data points based on the way we've decided to design the experiment. All right, so let's go ahead and organize this for ease of data entry. All right, so to do that, we're going to go up to data, and we're going to go to sort. Now when we sort this, we're going to grab everything from C1 through C10, hold down the shift key, click on C10. I want to put it into the sort columns, and I am going to press the select button. Double clicking isn't going to work for you. Now what are we going to sort it by? Well, we're going to sort it by C10, the sort column. All right, we're going to put it back in the original columns. All right, and I'm going to say OK. And now notice that we have all of the run number 1s together, the run number 2s, the run number 3s, 4s, etc. So now we're ready to do our data entry, which what we would then do is we would have our data column, and actually that would be tool life. And we're measuring that in inches of bit life. So, all right, so that would be the layout to get the design into a format that's ready to run. Then one of the things that you could do if you're going to run this experiment, you could take 8 pennies, and with a Sharpie you write 1 through 8 on the pennies, take the pennies, throw them into a baseball hat, shake them up, have different members of your team, select a penny, and then that penny becomes, the order that you grab those out, that's the randomized order, and then you can actually run your experiment in that order. All right, but our data entry is going to be easy because we already have all of our experimental conditions. The similar conditions are all next to each other, so it's going to be easy to put the data in. All right, so now let's go ahead and click on the Show Worksheets folder. And now what we're going to do is we're going to open up the Multiple Rep Interactions DOE. We're going to open that up. All right, so this is already set up. It already has all of the data in. All right, all the data has been entered. And we are in a position where we can go ahead and conduct our analysis. All right, so everything's there. So let's go ahead and do our analysis on this experiment. All right, so to do that, we're going to go up to Stat, DOE. All right, it's a factorial, and we are going to analyze this factorial design. All right, so C10 is the response. The terms that we are going to include, all right, I'm going to take the terms out. So we're going to have the XY feed, we're going to have the stack height, we're going to have the speed, we're going to have the bit type, we're going to have the suction. Now notice that Minitab is giving us A, B, A, C, B, C, B, D, A, B, C. It's giving us all of this stuff that it's saying we could study. Well, guess what? We know that we can't. All right, because we already know the design that we selected. We know what we can and cannot study. We know that we can place 5 factors into this particular design layout, and we can study one combined effect. And we have chosen that we're going to study that B times C combined effects. We're going to pick B times C. All right, so now we have it set up to analyze it based on the way that we designed it. All right, so Minitab is giving us all of the possible options, even though some of those we would have confounding. So we are smarter than that. We know the design. We know how we're going to use it. So we've got it all set up. We'll say OK to that. Now, from a results standpoint, we want to have all of the results. We want the coefficients and analysis variance table, because this is the first initial run of the design experiment. So we don't know what we're going to be pooling, but we do know that there will be a reduction of factors after we do this initial experiment run. All right, so we're going to do our first analysis, and then we'll review the factors and determine which ones get pooled into the unexplained, which ones we're going to keep, and then we'll run it a second time, and then we'll be finished. So we'll run it the first time. All right, and we can see that when we look at our Pareto chart of standardized effects, and this red line here, that's basically a 0.05 p-value. So anything that's beyond that has a significance of at least 95%. So that's a really good thing. We got 95% confidence in those things, significant at a p-value of 0.05. All right, so factor B, that's a strong factor. The B times C combined effect. A is a strong factor. All right, well, if I'm going to keep B and BC, even though C is not significant, because we have it as part of the combined effect in B times C, we're going to keep it in the model. But factors E and D are going to be pooled. We're going to remove those from the model because they are not going to really turn out to give us any big benefit whatsoever. All right, so those two are going to get pooled. We can take a look at the session window. If I go up to the big blue eye, I can go right to the session window, and I can scroll up, and we can take a look at the statistics that we have. And here we have the T statistics that we're going to look at, and we know that if we have a T statistic that's at an absolute value of 1 or less, that it should get pooled into the unexplained. Well, that's speed, factor C, but we're keeping that because we've got the BC interaction. All right, but factors D and E, based on our, based on this, factors D and E, based on our Pareto chart, we are going to take those out of the model. So D and E are coming out, and factors D and E, that's our bit type and our suction foot type. So what we can do is we can rerun our model here, edit last dialog box, and we're still going to look at bit life. The terms now, we're going to take D out, we're going to take suction foot out, so we're keeping A and B, and we're going to keep the BC combined effect. Now we do know that if a combined effect is significant, it will take precedent over the single effects taken alone. So sometimes, there are times when the combined effect is going to give us different level settings than the single effect taken alone. In this case, we know that that's for a fact because C would have been pulled because it's insignificant, but it's part of the BC interaction, so it's a strong factor now. We're going to have to keep it in the model. All right, we're going to check the terms to make sure that we have everything we're supposed to, A, B, C, and the BC interaction. And now we're going to say OK. So there's our standardized effects. We knew what that was going to be like. We'd already seen that. And now we're going to scroll up. And we can see that we've got a significant model for both main effects and interactions. P-values are very, very low, 0.000 some number, very, very small. We actually have a regression model equation that can be used for prediction. We'll do in a little bit. All right, and we can see that all of our factors, the XY feed, the stack height times speed, are all significant. We did not expect factor C to be significant, but it has to be part of the model because it's part of that combined effect. All right, now we're going to grab something from here right now. We have a standard deviation of 1.6. So we're going to write that down. And we're going to need that because once we make a prediction, that'll give us an estimate of the standard deviation about the predicted value. All right. Now, another thing that we can do to help us to understand what we're comparing against is we can go back to our worksheet, and we're going to make that worksheet, we're going to make it big again. I'm going to scroll over here, and we've got the bit life. So let's go ahead and we'll do some basic statistics. We're going to display some descriptive statistics, and we want bit life. And what we'd like to see on the bit life is the average and the standard deviation. So we're going to go ahead and calculate that because we're going to use that as a comparative a little bit later. All right, so we've got that. So we're going to write that thing down. And it says that before we changed anything, overall, based on all the variation that we had of all the level settings and different factors, we had an average bit life of 21.5 and a standard deviation of 4.4. All right. So we're going to use that as a comparative a little bit later. Now, one of the things that we can do is let's find out what's the best settings for the factors that are significant. So if we go back to our session window, scroll up a little bit, all right, we can see that we have an XY feed, stack height, and then we have this combined effect. Now we can look at the numbers, and here's the average values, or we can look at some graphs. All right, so let's graph this stuff and take a look at that. It's often easier just to pick it off of a graph, although you can see the results and the answers right here. Let's go ahead and do the graphic. So it's going to be stat, DOE, factorial, and we are going to do our factorial plots. And we have a main effects plot. We got to set that up. We want bit life. And what we want to have in bit life is A and B. All right. And we're going to say OK to that. And then for the interaction plot, we're going to set that up. And we want the BC combined effect. And we're going to say OK to that. And then let's go ahead and plot these. So from the combined effect of B times C, and if we're trying to maximize the bit life, it's telling us that we want to have a speed of 40, all right, speed of 40, and a stack height of 0.1875. The 0.1875 is the black line, and so if I'm at 0.1875 and a speed of 40, you know, I can see that my my average bit life is going to be, you know, close to 27. All right, so we are going to be selecting a stack height of 0.1875. We're going to have a speed of 40. And now let's see what it says about the XY feed. So we can go to our big blue eye and go left to the Show the Worksheets folder. Actually, too far. We only want to go to the Graphics folder. Sorry about that. Main Effects Plot. I'll make that big. And so it says the XY feed, we want to be at a value of 60 because 60 is going to maximize our XY feed. And also the stack height should be at 0.1875, which we saw from the combined effect, but we're also seeing that from a single effect taken by itself as well. And factor C would not have made a difference, so we didn't bother to look at that one. All right, so now we know the significant factors and we know the best level settings. The next thing to take a look at would be what would be a prediction of where we would be if we chose all of this stuff. So what we can do is go back to Stat and DOE and Factorial, and then we come down here to this thing called the Response Optimizer. And yes, we're going to take a look at BitLife. We're going to set that up. We want to maximize it. We have a lower value of 20, a target value of 30. All right, and we're trying to maximize the bit life. And we're going to say OK. And we're going to go ahead and say OK. So now what we have is it's telling us from a desirability standpoint, we should be at an XY feed of 60, stack height of 0.1875, a speed of 40, which is the level settings that we knew were the ones that were significant and the best settings. It's giving us a prediction of the bit life, and it's saying that that should be at 28.347. All right, now the desirability index is a measure of how good you predicted what we're trying to hit for a target as far as maximizing. Now we said we're going to try to get to 30. We didn't quite get to 30. We got to 28.34. All right, so it's telling us that our desirability is 0.83. If we had made a poorer guess, we would still get this prediction and our desirability would have been less. So it's an interesting statistic. It doesn't really do much for us. Now, one thing that is interesting, though, is let's say that we had a new material came in and it wasn't 0.1875. It was actually thicker. So we could actually move this to a thicker stack height, and then that will give us an idea of what our bit life is going to be because we just changed that. So the Response Optimizer gives you the ability to play around a little bit, okay, at least within the range of the low and high settings for the factors that were in the design experiment, because this is based on a regression model. So within the ranges that were in there, you can make some predictions as to what will take place. So that's pretty cool. All right, so now we know that we should see a bit life of 28.34. We should see a standard deviation of 1.6. And let's see what that looks like when we compare it against the original, which was 28.5 for bit life with a standard deviation of 4.4. All right, so if we're going to do that, let's go up to Big Blue Eye. Let's move over to our worksheet folder. And let's just go ahead and pick one of these worksheets. Grab number 5. And let's just call this one our prediction. And we'll say this was here's our baseline. All right, so there's our prediction, there's our baseline. So what we're going to do is we're going to generate 50 data points given the mean and standard deviation from each of these. So to do that, I'm going to go to Calc, I'm going to go to Random Data, I am going to generate some normally distributed data, which is off your screen, but it's up at the top of this column. Pick normally distributed data. I'm going to have 50 data points. I'm going to put it in the prediction column. As you can see, when you save a Minitab project, it remembers everything you put in there. 28.34 with standard deviation of 1.6. And I'm going to say OK. And then the next thing, I'm going to do this one more time. Edit last dialog box, and this time I'm going to put it into the baseline, and the baseline is 21.5, and the standard deviation on the baseline is 4.4. I'm going to say OK. And now what we're going to do is I'm just going to generate a histogram so you can see the difference between the baseline and the prediction, and you can see the improvement that we've just gotten from our design experiments. So let's take a look at that. So that's going to be a graph, a histogram. We're going to select the ones called with, fit, and groups. And it's going to be prediction, baseline, are the graph variables, and I'm just going to say OK. I'll make this big so you can see it. And look at the difference. Here's the baseline. Look at the variability in the baseline. And here's, you can see where the average is, and a lot of variation. And then look what we've done with the design experiment. We've not only shifted the average value dramatically, but we've also dramatically reduced the variability about that average. And that's what design of experiments is all about. Get yourself to a better situation, whether it's minimizing, maximizing, or hitting a target, and then reducing the variability about that value. So that's the end of our fractional factorial with one interaction experiment example, and you've seen how to do it in Minitab.